This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about virtual one-on-one MCAT tutoring. In this video, we're going to cover the other gas laws that were not covered in the ideal gas law video, and this will cover partial pressures and Henry's law that deals with gas solubility. The first critical thing to understand when talking about partial pressure is the idea that all gases contribute the same amount of pressure per mole. So if you have a container and you have 10 moles of oxygen in it and you have 10 moles of nitrogen, they're both contributing the same amount of pressure. So the identity of a gas does not change how much pressure that gas contributes. It's only dependent on how much of that gas we have. What that means is if you have a mixture of gas molecules, so you have a bunch of different types of gases, and if you think of atmospheric air as your example, it works really well. We have nitrogen, we have oxygen, we have CO2. So atmospheric air is a mixture of a bunch of gases. If we picked one of those types of gases, and we'll just call it A, and you find the number of moles of gas A and divide it by the total number of moles of your gas mixture, that's going to give you the molar fraction of A, of gas A, which is represented by this X subscript A. Then if you take that molar fraction and multiply it by the total pressure, so however much pressure your total amount of gases are creating, multiply that molar fraction by it, and you will get the pressure that just gas A is contributing. And this works because of the fact that all gases contribute the same amount of pressure per mole. And that also gives us this last idea, which is if you were to add up all of the partial pressures of all of your gases, then you're going to get the total pressure. So here we have pressure of gas A plus pressure of gas B plus pressure of gas C, and then so on for however many gases you have. If you add them all up, you're going to get the total pressure of that mixture of gases. So let's look at our example on the bottom, which is a real-life example of air. So 78% of air is nitrogen. And if we're asked what is the partial pressure of nitrogen, we want to take the molar fraction, which is going to be 0.78 from that 78%, multiply that by the total pressure that's in the atmosphere, which would just be 1 atmosphere. So then the total pressure that nitrogen is contributing to atmospheric pressure is 0.78 atmospheres. We could continue this with oxygen. So oxygen is about 21%. So you do 0.21 times 1 atm, and that would give you 0.21 atms. And then the rest of air is basically just a combination of other gases. So we only have 1% left. So it would be 0.01 times 1 atmosphere equals 0.01 atmospheres, and that's from the other gases. So if we wanted to practice our second equation that we talked about, we would do pressure of nitrogen, so P and then N plus PO2, because oxygen gas is a diatomic molecule, plus P, and then I'll just put M for mixture. And then that should equal the total pressure, which we said was 1 atm. And then if we fill in our values, that is 0.78 plus 0.21 plus 0.01, which does equal 1. Henry's law takes the idea of partial pressure and then applies it to the solubility of a gas. And the first concept that you want to be really comfortable with is the idea that if a gas and a liquid are in contact, some of the gas is going to dissolve into that liquid. And the amount that dissolves is very dependent on what your gas is and what your liquid is, and it's also dependent on the pressure of that gas. And both of these things are represented by this equation we have here, which is Henry's law. Henry's law shows us the concentration of A, which is just our made-up gas. So how much of A has dissolved into the liquid is equal to this KH, which KH will be dependent on the type of gas and the type of liquid. So that's going to be a given. And then you multiply KH by the partial pressure of A. So you can see that as the partial pressure of gas A goes up, the amount of gas A that is then dissolved into the liquid also goes up. This equation is really easy to apply whenever you're given the numbers, but you also want to make sure that you're able to just think through how this equation would apply to real-life systems. So here we're going to apply it to the respiratory and circulatory systems. The question is asking us, what happens to the amount of CO2 that's dissolved in the blood that is near tissues during exercise? The first thing you want to think about is during exercise, you are doing a lot more biochemical reactions that are producing CO2. So you're producing CO2 through things like the Krebs cycle and converting pyruvate to acetyl coenzyme A, and you're doing all this to produce more ATP. So that means that CO2, the amount of CO2 in the tissues, is going up. In other words, the pressure of CO2 in the tissues is going up. And remember that capillaries are integrated into tissues and they run throughout tissues and they're in direct contact with pretty much every part of your body. So if I draw just a square here to represent the tissue, this tissue now has a higher concentration of CO2. So the pressure of CO2 in that tissue has gone up. And then right next to that tissue, we have capillary systems. So in the blood that is in this vessel I just drew, we are asked what happens to the amount of CO2 that is dissolved into that blood. CO2 is able to cross through cell membranes, so if there's enough CO2 in the tissue, it can travel into the bloodstream. So what would happen to the concentration of CO2 when the amount of CO2 is increasing in the tissue? And we said that the pressure of CO2 is going up. KH will be constant. Nothing's going to change with that. And then CO2 dissolved in the blood will now go up according to that equation. So Henry's law gives us a very definitive way to explain why CO2 dissolves into the blood during exercise. And when you get into the cardiovascular system, you'll probably learn more about the bicarb buffer system. But for now, we're not going to talk about that. We're just going to say CO2 dissolves into the blood more during exercise and leave it at that. This last question is asking you to apply the exact same idea, but to a slightly different situation where we are exhaling CO2 and then seeing what happens to the amount of CO2 that's in the blood, in the blood vessels or the capillaries that are surrounding the lung. So the first thing you want to think about is the pressure of CO2. We said CO2 is leaving the lung because we are exhaling, so that means that the pressure of CO2 is going down. So now just write out your equation, which was the concentration of CO2 is equal to that constant, which will not change, times the pressure of CO2. And we've said the pressure is going down. So if the pressure of CO2 goes down, then that means that the concentration of CO2 in the blood must also go down. And when that's going down, ask yourself, well, what's happening to it? The CO2 is going from dissolved CO2 to gas CO2. So that means that more CO2 is leaving the fluid or the blood that's around your lungs and going into your lungs. So as you exhale, it's allowing your blood to release more CO2 into your lungs. So then that allows for more efficient exchange of CO2 and getting rid of more CO2 out of your blood. And you could apply the same thing to oxygen whenever you inhale. When you inhale, the partial pressure of oxygen goes up a lot. So then that allows for oxygen to dissolve into the blood. And then when that blood that's rich in oxygen gets to the tissues, those tissues don't have any oxygen in them because it's all being used up. So then the partial pressure of oxygen around the tissues is really low, which then allows for oxygen to leave the blood and then enter the tissue. So you want to be really comfortable applying Henry's law to gas exchange in the body. It's a really common thing that you're very likely going to have to be able to think through on test day.